Okay, in this video, we're going to talk about section 3.5 dealing with derivatives of trigonometric functions. Derivatives of trigonometric functions. Now, in this section, we're going to be talking about first how to find the limits of trigonometric functions. So we're going to be finding limits that involve trigonometric functions. Then we're going to find derivatives of the basic trigonometric functions, and also we're going to find derivatives that involve trigonometric functions. So that's the basis of section 3.5. All right, so we're going to begin with two special limits, okay? So here we have trigonometric limits, and they are this. If I have the limit as x approaches 0 of sine of x divided by x, that's going to be equal to 1. And also the limit as x approaches 0 of the cosine of x minus 1 divided by x will be equal to 0. Okay. Now, the proof of these two are going to be time consuming. So pretty much there are videos out there that does give a proof that the limit as x approaches 0 of sine of x divided by x is 1. And the limit as x approaches 0 of cosine x minus 1 divided by x is equal to 0. Okay, but we're going to use these to evaluate limits here, like in part A of example 1. Here we got the limit as x approaches 0 of the sine of x divided by 13x. Okay, now, in this case here, the coefficient of 1, the coefficient in front of the sine of x, that's going to be 1. Okay. Now, with that problem, I'm going to use the constant multiple rule where if I have the limit as x approaches some constant of c times f of x, I can pull the constant out in front and then take the limit of the function containing x in it. So this is like 1 over 13. So I'm going to pull the 1/13 out in front, and then I'll have the limit as it approaches 0 of sine x divided by x. And that limit as x approaches 0 of sine x divided by x is this right here, and it equals to 1. So I have the 1/13 times 1, which ends up being 1 over 13. So the limit as x approaches 0 of sine x divided by 13x will be 1 over 13. Okay, so that's part A. Now let's take a look at part B. Here we got the limit as x approaches 0 of sine of 8x divided by the sine of 9x. All right, now first of all, what I need to do here is write this in a way that I will have the limit as x approaches 0 of sine of x divided by x. So I know I'm going to need an x in the denominator and in the numerator. Well, actually, I need 1 over x in the denominator and in the numerator. So what I'm going to do here is multiply the numerator by 1 over x and the denominator by 1 over x. So here's what I'm going to have. The limit as x approaches 0 of, now in the numerator, I'm going to have sine of 8x all over x. That's going to be divided by the sine of 9x divided by x. Now, in this case here, notice I got 8x in the numerator. The denominator, I need to have 8x. So that way I can take the limit as x approaches 0 of sine of whatever x is over whatever x is. These two have to be the same. I do have the x, but I'm missing the 8. So what I need to do here is multiply in the numerator, and in the denominator, I need to multiply by 8 over 8. Now take a look at your denominator, sine of 9x over x. This x in here needs to be a 9. So to do that, I need to multiply the numerator and the denominator by 9. So here's what I'm going to have. The limit as x approaches 0 of 8 times sine 8x would be, let me put this in bracket, 8 sine x divided by 8x. The denominator will be 9 times sine x over, sine 9 times sine 9x. This should be 8x as well. Don't want to leave that out. And that's 1 sine 9 times sine 9x over 9x. Okay. Sometimes in this case, I had to manipulate this in a way so that this is the same as this, and also this being the same as that. Okay, now, the limit of a quotient, that means I can simplify that by doing the quotient of the individual limit. So I can do the limit as x approaches 0 of, and by the way, this 8 is a constant right here. So that means I can pull the 8 out in front. So it'll be 8 times the limit as x approaches 0 of sine 8x over 8x. The denominator, I'm going to do the same thing. The 9 is a constant. I can pull the 9 out in front. And the denominator, I have the limit as x approaches 0 of sine 9x over 9x. Okay, so this follows the theorem that the limit as x approaches 0 of sine of x over x equals to 1. Here, these two are the same. So the limit as x approaches 0 of sine of 8x times 8x divided by 8x will be 1. So in the numerator, I'm going to have 8 times 1 divided by the denominator. I bring over the 9, the same thing. The sine of this angle is the same as the 9x down here. So the limit as x approaches 0 of sine 9x divided by 9 will also be 1. Then 8 times 1 will be 8, and 9 times 1 will be 9. So the limit as x approaches 0 of sine of 8x divided by sine of 9x will be 8 over 9. Okay. Now part C deals with the cosine. So here we got the limit as theta approaches 0, cosine squared 0 minus 1 divided by theta. Okay, in this case here, let's bring over the limit as theta approaches 0. That cosine squared theta minus 1, that's the difference of 2 perfect squares. I can factor that into the sum and the difference of the same 2 terms. Cosine squared theta breaks up as cosine theta times cosine theta, and 1 would just be 1 times 1. And it's a difference of 2 squares. One must be plus, the other one must be minus. That's divided by theta. Okay. Now I'm going to bring down the limit as theta approaches 0. Now I'm going to break this up into 2 separate parts. One will be the cosine theta plus 1 over 1 times cosine theta minus 1 divided by theta. Okay, because if I multiply this numerator times this numerator, I get this, then 1 times theta would be theta. So I'm breaking it up like this. Now, if I take the limit of a product That's going to be the product of their individual limits. So here, I have the limit as theta approaches 0, a cosine theta plus 1 times the limit as theta approaches 0 of cosine theta minus 1 divided by theta. But this part right here, I can use direct substitution, okay? Because I know something about the cosine of 0. Now you have to go back to your unit circle to find out what cosine of 0 is. Actually, I don't need this. I don't need that limit notation. I'm going to white out this. I'm just do direct substitution here. So this will be cosine. And I'm letting theta be 0 and then plus 1. Times, now the limit is theta approaches 0, cosine theta minus 1 divided by theta. That is this trig limit. It's going to be equal to 0. Okay, here we're just using theta. So the limit is theta approaches 0, cosine theta minus 1 divided by theta would end up being 0. Now, from your unit circle, the cosine of 0 is 1. And of course, 1 plus 1 would be 2. 2 times 0 is 0. So the limit is theta approaches 0 of cosine squared theta minus 1 divided by theta will end up being 0. Okay. Now for cosine theta, you have to refer back to chapter 1 when we talked about the unit circle. Because x is always going to be the cosine theta. X will always be your cosine, y will be your sine. All right, here's one more of these. Let's use the limit as theta approaches 0, sine of x divided by x equaling to 1 to evaluate this limit as x approaches 10 of sine of the quantity x minus 10 divided by x squared minus 100. Okay. So I'm going to start with the limit as x approaches 10 of sine of the quantity x minus 10 divided by x squared minus 100. All right, so I'm going to bring over the limit as x approaches 10. The numerator will still be sine of the quantity x minus 10. If you look at your denominator, x squared minus 100 is a difference of 2 perfect squares. I can factor that into 2 binomials. X squared breaks up as x and x. 10, what number squared gives you 10? I mean, what number squared gives you 100? I think I gave it away. It's 10. So 10 times 10 is 100. And one has to be plus, the other one has to be minus for it to be differences of 2 perfect squares. Okay. Now we're going to break this up into two parts. I'm going to bring over the limit as x approaches 10 of, here I got the sine of the quantity x minus 10. That's going to be divided by, and I get x minus 10 in the denominator. So I'm going to put that x minus 10 with the sine of the quantity x minus 10. That would be multiplied by 1 over x plus 10. So sine of x minus 10 times the 1 would give me this back. X minus 10 times x plus 10 is this. Now, I have the limit of a product that's equivalent to the product of their individual limits. So here I got the limit as x approaches 10 of sine of the quantity x minus 10 divided by x minus 10. Then that's multiplied by the limit as x approaches 10 of 1 over x plus 10. Now, if I take the limit as x approaches 10 of the sine of this x minus 10 divided by x minus 10, it follows this rule here. It's going to be equal to 1. So this will be 1 times, and then we can do direct substitution for this limit as x approaches 10 of 1 over x plus 10, because I'm not going to get a 0 in the denominator. So let's go ahead and do direct substitution. That's going to be 1 over 10 plus 10. And then 1 times 1 over 10 plus 10, which is 20. 1 times 1 over 20 would be 1 over 20. So the limit as x approaches 10 of sine of the quantity x minus 10 divided by x squared minus 100 will be 1 over 20. Okay. So this is how we use trigonometric limits for sine and cosine. Now for the derivatives of sine and cosine, here they are. Here's just for sine and cosine. We'll talk about the other 4 later. The derivative with respect to x of sine of x will be equal to the cosine of x, and the derivative of the cosine of x with respect to x would be equal to negative sine x. Okay. Now I'm just going to prove that the derivative of the sine of x would give you the cosine of x. Okay. Now here's what I'm going to do. I'm going to let f of x be equal to the sine of x. F of x will be equal to the sine of x. Now I'm going to use that definition formula for a limit. That's this, f prime of x is equal to, and if you recall, the limit as h approaches 0 of f of x plus h minus f of x, all that's divided by h. And then we do our substitution here. F prime of x would be this, the limit as h approaches 0 of f of x plus h. I'm just going to replace that x in sine of x with the x plus h. So it'll be sine of the quantity x plus h minus f of x, which is the sine of x, all divided by h. Okay. Now, for this sine of x plus h, that's one of those sum and difference identities. So here, if you recall, if I have the sine of a plus b, that is going to be the same as this, the sine of a times the cosine of b, and then plus the cosine of a sine of b. That's one of those that's one of those sum and difference identities that we talked about back in section 1.4. So you might want to refer to your notes in section 1.4 that talks about this sum and difference identity. And it's this, for sine of a plus b. Now in this case here, I will use this to expand the sine of the quantity x plus h. In this case here will be the sine of the first, which is x, times the cosine of the second, which is h, then plus the cosine of x sine h. And I still got minus sine of x. I need to bring that down. All that's divided by h. All right, now for the limit as h approaches 0. Now this is what I'm going to do with this problem here. I'm going to group terms that have sine of h in them. This term with this term right here, sine of x, sine of x. I'm going to group that together. So here I got sine of x, cosine of h, and then minus sine of x. That's going to be divided by h. And then this will be plus the cosine of x, sine of h, all divided by h. Here I'm grouping terms that have the sine of x in them. Because you're going to see what's going to happen here is I'm going to take out the sine of x because that's the common factor. So here, the limit as h approaches 0 of, if I factor out sine of x, oops, don't need the parentheses here. Sine of x, just factor out the sine of x, then I'm going to have this. I'll be left with cosine of h minus sine of x divided by itself will be 1. That's going to be over h. And then plus, and I'm also going to do this. If I have the limit of the sum, I can write this as the sum of their individual limits. So this part will have a limit as h approaches 0 of cosine x sine h, all divided by h. Now, the sine of x does not have an h in it, so that's treated as a constant. So I'm going to pull the sine of x out in front, and then that will be multiplied by the limit as h approaches 0 of the cosine of h minus 1 divided by h. The same thing here. The cosine of x does not have h in it. That's going to be a constant as well. So I can pull the cosine of x out in front, and then that's multiplied by the limit as h approaches 0 of sine of h divided by h. Okay, now I'm going to use those trigonometric limits here that we talked about here. For this one, the limit is h approaches 0, cosine of h minus 1 divided by h follows this limit right here. That's going to be equal to 0. So I got sine of x times 0, and then plus cosine of x times the limit as h approaches 0, sine of h over h. That's the other trigonometric limit. That's going to be equal to 1. Sine of x times 0 is 0. Cosine of x times 1 will be cosine of x. Add that to 0, you'll end up with the cosine of x. Okay, so that's the proof that the derivative with respect to x of sine of x will be equal to cosine of x. And we can use the same procedure with cosine of x, find its derivative, and you'll end up with negative sine of x. Okay. Now, we won't have time to go through that as well, because that'll take up a lot of time to do that. Okay. So let's start with this. Y is equal to 2 sine of x plus 5 cosine of x. So we're going to use those two derivatives to find the derivative of this function or this equation. So we're finding dy dx. All right, so here we bring down the constant, which is your 2. The derivative of sine of x will be cosine of x plus, bring down the 5. The derivative of the cosine of x is negative sine of x. Now, if we just simplify this, this will be 2 cosine of x. We'll say minus 5 sine of x. Okay, so all I'm doing there is just using the derivative of the sine, which is your cosine, and the derivative of the cosine, which is negative sine of x. All right, part B, y equals 16x plus the cosine of 7x. Okay. For 16x, its derivative would just be 16. Then plus, bring down the 7, take the derivative of the cosine, that'll end up being negative sine of x. And if we simplify this, this will be just 16 minus 7 sine of x. Okay, that's the derivative of y equals 16x plus 7 cosine of x. 16 minus 7 sine of x. All right, now let's look at part C. We got y equal e to the negative 3x times the sine of x. Well, e to the negative 3x is multiplied by the sine of x, so that tells me I need to use the product rule. And of course, the product rule is this. My first term is going to be e to the negative 3x. And then the second term would just be sine of x. So if the first is going to be negative 3x, e to the negative 3x, the derivative of the first will have to be, and if you recall, the derivative of e to the kx would be that constant k multiplied by e to the negative kx. Here, for e to the negative 3x, its derivative will be that negative 3 goes in front, and then we copy over the e to the negative 3x. That's your derivative. And then for the second term being the sine of x, the derivative of the sine of x is the cosine of x. So here we're going to use the product rule. That's this. First times the derivative of the second. That's your e to the negative 3x times the derivative of the second, which is your cosine, plus the second, which is sine of x, times the derivative of the first. That's negative 3 e to the negative 3x. I'm going to bring down e to the negative 3x times the cosine of x. Let's see. Plus a negative would be minus, so it'll be minus 3. Let me put minus 3 e to the negative 3x times the sine of x. I'll put the negative 3x in front. Now notice I got e to the negative 3x as a common factor. So let's factor e to the negative 3x out. And when I do that, I'll be left with the cosine of x minus, I'll be left with a 3 and a sine of x when I factor e to the negative 3x out. And this will be the final answer for the derivative of y equal e to the negative 3x sine of x. E to the negative 3x times the cosine x minus 3 sine of x. So in that case, I had to use the product rule for that problem. I take a look at part D. We got y equal 9 sine of x plus 5 times e to the 0.08x. Okay. So to find y prime, I'm going to bring down the 9, take the derivative of the sine of x, which is the cosine of x, plus bring down this 5. That e to the kx rule, if I take the derivative of e to the kx, that would be 0.8, and then copy over the e to the 0.8x. And then simplify this, I'll bring down the 9 cosine of x plus 5 times 0.8 would be 4. And then e to the 0.8x. So the derivative of y equals 9 sine of x plus 5 e to the 0.08x will be 9 cosine of x plus 4 e to the 0.8x. Okay. Now part E, again, we're going to have to use the product rule on this one. For y equal e to the 2x times the cosine of x. So let's identify the first and the second. The first would be your e to the 2x, and then your second would be cosine x. Well, the first is e to the 2x, and that means the derivative of that would be using the e to the 2x rule, e to the kx rule, that'd be 2 times e to the 2x. Okay, and then the derivative of the second, if the second is the cosine of x, the derivative of the cosine would be negative sine x. Okay. So to find the derivative, we just simply do first times the derivative of the second. The first is e to the 2x times the derivative of the second, that's negative sine of x, plus the second times the derivative of the first, the cosine x times the derivative of the second was 2e to the 2x. Now, if I simplify this a bit, I'll pull the negative in front of e to the 2x times the sine of x, plus, now I'll pull the 2 in front of the cosine of x, or do this. 2e to the 2x will go in front. 2e to the 2x times the cosine of x. And in this case here, I'm going to factor out a negative e to the 2x. Negative e to the 2x. When I do that, negative e to the 2x sine of x divided by e to the negative 2x will leave me with sine of x. Now, a positive divided by a negative will be a negative, and I've taken out e to the 2x, I'll be left with a 2 and a cosine of x. So the derivative there will be e to the negative 2x times the quantity sine of x minus 2 cosine of x. A couple more examples here. Now here we're going to have to use the quotient rule in part F. That's in this case, y equals 7 sine of x divided by 8 minus 9 times the sine of x. So we have to use the quotient rule. We need to identify the high, which is the numerator of 7 sine of x, and the low, that's the denominator, 8 minus 9 sine of x. All right, so let's take the derivative of the high. If the high is 7 sine of x, its derivative will be 7 times the cosine of x. If the low is 8 minus 9 sine of x, its derivative will have to be, the derivative of 8 is 0, and then we have the minus. 9 sine of x, we bring down the 9, its derivative of sine of x will be the cosine of x. Okay. So now dy dx, or y prime, doesn't matter, it's going to be low times the derivative of the high. That's going to be the 8 minus 9 sine x. Eight minus 9 sine of x times the derivative of the high, which is 7 cosine of x, minus the high, which is 7 sine of x, times the derivative of the low, that's negative 9 cosine of x. Now this whole thing will be divided by the square of the low. That's your 8 minus 9 sine of x. This quantity is squared. All right, now we're going to have to simplify all of this here. Let's see, distribute the 7 cosine of x over the 8 minus 9 sine of x. 7 cosine of x times 8. That would be 56 times the cosine of x. And then 7 cosine of x times the minus 9 sine of x would be minus 63 sine x cosine x. Now, this minus times this minus will make that a plus. Then 7 times 9 would be 63, and then times the sine of x, cosine of x. All that's divided by the quantity 8 minus 9 sine of x, and that's squared. Now, in this case here, notice that we got minus 63 sine cosine of x and plus 63 sine cosine of x. That adds to 0. That's gone. All you'll be left with is, in the numerator, 56 times the cosine of x. All that's divided by the quantity 8 minus 9 sine of x, and that's squared. Okay. All right, now part G. Here we got y equals 12 cosine x sine of x. And he'll want to find this derivative. Well, cosine x times sine of x, that tells me I need to use the product rule here. So for dy dx, the constant, I can bring this down. But for the cosine x times the sine of x, this will be the first, which is the cosine of x, times the derivative of the second. The derivative of the sine of x is going to be cosine of x, plus the second, which is sine x, times the derivative of the first. The derivative of the cosine is negative sine x. Now, if you wanted to, you can just label the first as cosine of x and the second as sine of x. And then take its derivative using that product rule. All right, bring down this 12. Cosine of x times the cosine of x will be cosine square x. The plus and the negative will make that plus or minus. Sine of x times sine of x will be sine square x. And I will go no further with that problem. So it'll be 12 times the quantity cosine square x minus sine square x. Okay. All right, so those are just examples where you were dealing with only taking the derivatives of the sine and the cosine functions. Now, here are the other derivatives for trigonometric functions. Okay, for the sake of time, I'll just go through each one of those, but I'm not going to have time to prove every one of them. But I know this, the first and the second, these two right here, you can prove by using the sum and trig identities. The other four, you can use the quotient rule by writing an equivalent function for that. The tangent would be something like sine over cosine. You can use the quotient rule for that. Cotangent is cosine over sine. Secant is one over the cosine, and cosecant is one over the sine. All right, so we've already talked about these first two. The derivative of the sine of x is cosine of x, and the derivative of the cosine of x is negative sine of x. Now for the tangent, its derivative will be secant square of x. And then for cotangent, its derivative will be negative cosecant square x. And then the derivative of secant x will be secant x times the tangent of x. And then for the cosecant of x, its derivative will be negative cosecant of x. cotangent of x. All right, so now, here's some examples of just this. All right, let's say we want to find the derivative of y equal 2 secant x plus the cosecant of x. And that's using these trig functions here that I just gave you. All right, so I'm going to use dy dx as a notation for the derivative. Bring this 2 down. The derivative of the secant is this, secant x tangent of x. Then plus the derivative of the cosecant of x, that's this part right here. That's going to be negative cosecant x cotangent x. So all I'm doing here is using these trig derivatives to find the derivative of that function. Now, bring down the 2 secant of x tangent of x. The minus will make this, the negative will make that plus or minus. So it'd be negative minus cosecant x cotangent x. And that's as far as I can go with that problem. So the derivative of y would be 2 secant x tangent x minus cosecant x cotangent x. All right, now part B is finding the derivative of r with respect to theta. For r is equal to the tangent theta times the secant of theta. Okay, now this might take a while for this one, because here we got r is equal to tangent theta times the secant of theta. And to find dr d theta, this one we got to use the product rule, because we got tangent theta times the secant of theta. And if you recall the product rule, it's going to be this, the first term, which is tangent, times the derivative of the second. The derivative of secant theta is, in this case, secant theta tangent theta. And then plus the second, which is secant theta, times the derivative of the first. Your derivative of the tangent is secant squared theta. Okay. And we're going to simplify all of this. Let's see. Bring down secant of theta times the derivative. Well, tangent theta times tangent theta is tangent square theta. And then plus secant theta times secant squared theta, the secant cube of theta. Okay. All right, next I'm going to simplify this right here, because they might want that final answer in terms of final answer in simplest form. Secant theta, if you recall one of your reciprocal identities, secant theta is 1 over the cosine of theta. So I'm going to write secant theta as 1 over the cosine of theta times the tangent theta, tangent squared theta. Well, tangent of theta is going to be sine of theta divided by the cosine of theta. So tangent squared theta will be sine squared theta divided by cosine squared theta plus secant cube of theta. All right, so if I multiply this, 1 times sine squared of theta will be sine squared theta divided by cosine theta times cosine squared theta will be cosine cube of theta plus the secant cube of theta. Now, what I'm going to do is break this up as sine squared theta. That's going to be multiplied by 1 over the cosine cube of theta. And there is an inverse identity, a reciprocal identity, where if I have 1 over the cosine cube of theta, or just plain 1 over the cosine of theta, would be the sine of theta. Not sine, secant of, secant of theta. 1 over the cosine of theta is the secant of theta. So 1 over cosine cube of theta would be the secant cube of theta. So I'm bringing down sine squared theta times secant cube theta plus secant cube theta. And here you'll see the common factor, secant cube of theta. If I factor that out, I'll be left with this, in this term, I'll be left with sine squared theta plus secant cube theta divided by itself will be 1. That's how they want you to simplify this. Okay. So in simplified form, the derivative of r with respect to theta would be the secant cube of theta times sine squared theta plus 1. Okay. All right, and here's one more of these examples here. This one we need to apply the quotient rule for y equal cosine x divided by 1 plus cosine of x. All right, so dy dx is this. Of course, it's going to be the low times the derivative of the high. So we write the low, which is your denominator, 1 plus cosine of x, times the derivative of the high. The derivative of cosine of x will be negative sine x minus the high, which is your cosine of x, times the derivative of the low. The derivative of 1 plus cosine of x, well, the derivative of 1 is 0. The derivative of cosine of x is negative sine x, all divided by the square of the low, 1 plus the cosine of x, and that's going to be squared. Okay. All right, next we'll simplify this if we can. Distribute that negative sine x over the 1 plus cosine of x, so negative sine of x times 1, negative sine x, negative sine x times plus cosine of x would be minus cosine x sine x. I like the cosine of x in front. Minus a negative will make that a plus, and then cosine of x, sine of x. All that's divided by 1 plus cosine of x, quantity squared. Well, notice that minus cosine x sine of x and plus cosine x sine of x adds to 0. That's gone. All you're left in the numerator is negative sine of x. So this will be negative sine of x divided by 1 plus cosine x squared, quantity squared. And that would be the final answer for the derivative of y. Negative sine of x divided by the quantity 1 plus cosine of x squared. Okay. All right, next we'll look at higher order trigonometric derivatives. Higher order trigonometric derivatives. Higher order derivatives of the sine and cosine functions are important in many applications. A few higher order derivatives of y equal sine of x reveal a pattern. Let's start with the y equals sine of x. If we take the first derivative of y, which is equal to sine of x. The derivative of sine of x, of course, that's the cosine of x. Now from that, we can take the second derivative of y with respect to x. So if the derivative of y is the cosine of x, then its second derivative would be this. The cosine of x is negative sine of x if you take that derivative. Okay. Now using this, we can take the third derivative. Okay. So I'm going to bring down the negative. The derivative of the sine of x is cosine of x. So the third derivative would be negative cosine of x. And finally, for the fourth derivative, okay, bring that negative sign down. The cosine of x, its derivative will be negative sine of x. But here, the negative of a negative will be positive. So this will end up being sine of x for the fourth derivative. Notice that when you take the fourth derivative of y equals sine of x, it's going to be the same as y equals sine of x. So you can see what that pattern is, how that pattern is going. So for every fourth derivative of y equals sine of x, it will be the sine of x. Now let's look at the cosine of x, y equals cosine of x. For the first derivative, the derivative of cosine of x will be negative sine x. Now for the second derivative, that means we need to take the derivative of the first derivative. That means we need to take the derivative of negative sine of x. Bring the negative side down, the derivative of sine of x will be cosine of x. Now we want the third derivative of y equals cosine of x. Well, let's look at the derivative, the second derivative here, which is negative cosine of x. So in this case here, I'm going to bring this negative down. Take the derivative of cosine of x, you're going to get negative sine of x. Well, negative of a negative makes that positive. So the third derivative would be sine of x. And finally, take the fourth derivative of this right here. The fourth derivative of y equals cosine of x. We need to look at the third derivative and take it. The derivative of sine of x will be cosine of x. Notice that for every fourth derivative of y equals cosine of x, it will be equal to what y is equal to, the cosine of x. Okay. Now this only works for sine, y equals sine of x, and y equals cosine of x. It's not going to work for the other four trigonometric functions, for tangent, cotangent, secant, and cosecant. Okay. Now let's look at some higher order derivatives so that way we can end this video here. Like finding y double prime of y equals 10x the sine of x. Okay, so we're starting off with y equals 10x times the sine of x. So in this case here, this will be the first and this will be the second. So you pretty much can guess that we're going to have to use the product rule on this problem right here. So if the first is 10x, that means its derivative will have to be 10. And if the second is the sine of x, then the derivative for that will have to be the cosine of x. Okay, if this helps, this is not necessary. So let's find y prime first. That's going to be first times the derivative of the second, which is going to be 10x times cosine of x. Because that's first times the derivative of the second plus the second times the derivative of the first, sine of x times 10. All right, so the first I'll have here 10x cosine of x plus I'll pull the 10 in front, so it'll be 10 times sine of x. And here I can factor out the 10, because that's in both of the terms. And if I do that, I will be left with x times the cosine of x plus sine of x. Okay. And that would be the first derivative of y equal 10x sine of x. Now let's find the second derivative of this. That's going to be y double prime. That means we need to take the derivative of the first derivative. So I'm going to bring the 10 down. This part, x times the cosine of x, I need to use the product rule again. So the product rule again will be this. First, which is your x, times the derivative of the cosine of x, which is, of course, negative sine of x, plus the second, which is cosine of x, times the derivative of the first, which is 1. And then plus the derivative of the sine of x is simply the cosine of x. All right, so y double prime, bring down the 10. I'll rewrite x times negative sine of x as negative x sine of x. Cosine of x times 1 would just be the cosine of x plus cosine of x. Now I'm going to combine like terms. I got 2 cosine of x's. So that's going to be negative x sine x plus 2 times the cosine of x, because I have 2 cosines of x's. And what I'll do is just distribute the 10 over everything in the parentheses. So this means I'm going to have y double prime equaling to negative 10x, negative 10x. So negative 10x sine x plus 10 times 2, that's 20. Bring over the cosine of x. Now you can write it like this. Put the 20 cosine of x in front, and then that'll be subtracted from 10x sine of x. And that will be what y double prime is of the function y equal 10x sine of x. That'd be equal to 20 cosine of x minus 10 sine of 10x sine of x. All right, now look at part B. We got y equal e to the 10x sine of x. And I want to find its second derivative. All right, in this case here, I again have to use the product rule on this one, because this part would be the first and this would be the second. So in that case there, that the first is going to be e to the 10x, its derivative will have to be, using the e to the kx theorem, it'd be 10 times e to the 10x. Okay, the coefficient of your x in the exponential part will be in front of your e. You copy over the e to the 10x. And if the second is the sine of x, well, that's a simple derivative. The derivative of the sine of x is the cosine of x. So now let's do y prime. That's going to be the first, which is e to the 10x, times the derivative of the second, which is your cosine of x, plus the second, which is sine of x, times the derivative of the first, which was 10 e to the 10x. Now, notice I have e to the 10x as a common factor. Let's go ahead and factor that out. When I do, I'll be left with cosine of x plus, and I'll be left with sine of x times 10, but I'm going to write that as 10 times the sine of x. So that's the first derivative. Now I'm going to use that to find the second derivative. And again, notice I got to use the product rule because I got e to the 10x times this part right here. So here's what y double prime will be. Again, this will be the first, so it'll be e to the 10x times the derivative of the second. Here, the derivative of the cosine is negative sine of x, plus, bring down the 10, the derivative of the sine of x is the cosine of x. First times the derivative of the second, and then plus this second, I'll write that down. Times the derivative of e to the 10x. And of course, that was 10 e to the 10x. Okay. We go first times the derivative of the second plus the second times the derivative of the first. Okay, so pretty much I'll let that be the first and this right here be the second. Now let's factor out that e to the 10x in this expression right here. So I'm pulling out the e to the 10x as a common factor. So if I take that e to the 10x out in this first term, I'm left with negative sine x times negative sine x plus 10 cosine of x plus, take out the e to the 10x, I'm going to have 10 times this, 10 times parentheses, cosine of x plus 10 sine of x. Now I'm going to distribute the 10 over the cosine of x plus 10 sine of x. So y double prime is equal to e to the 10x times, inside the bracket, negative sine of x plus 10 cosine of x. And then distribute the 10. This will be plus 10 cosine of x plus 10 times 10, that's 100 times the sine of x. Now we're going to combine some like terms in this bracket right here. So here we're going to have y double prime, and that's going to be equal to e to the 10x on the outside. Now, notice we got negative sine of x plus 100 sine of x. That's going to give us 99 sine of x plus 10 cosine of x plus another 10 cosine of x. That's 20 cosine of x. Okay. And then finally, I'll just distribute the e to the 10x over the 99 sine of x plus 20 cosine of x. So my final answer there will be 99 e to the 10x times sine of x plus 20 times e to the 10x cosine of x. So that is what y double prime will end up being. Okay, so sometimes you got to do a bit of algebra in order to get to that final answer. Okay. All right, so that's going to conclude this video on section 3.5 dealing with derivatives of trigonometric functions. Do feel free to contact me if you have any questions about any of the problems that were presented in this video or any of the questions in the homework on section 3.5 in my math lab.